Winglets are the distinctive vertical or near-vertical extensions found at the tips of modern aircraft wings, and they serve one primary purpose: to improve aircraft fuel efficiency by reducing aerodynamic drag. These small but sophisticated devices have become essential components of contemporary aviation, saving airlines billions of dollars in fuel costs while contributing to environmental sustainability. The fundamental physics behind winglets relates to how aircraft wings generate lift. When air flows over a wing, it creates higher pressure below and lower pressure above the wing's surface. At the wingtips, air from the high-pressure zone naturally spills around to the low-pressure area, creating rotating air patterns called wingtip vortices. These vortices generate induced drag, which forces aircraft engines to work harder and consume more fuel. Winglets function as aerodynamic barriers that reduce the formation of these wingtip vortices. By extending vertically from the wingtips, they effectively prevent the mixing of high and low-pressure airflows, weakening the vortices and subsequently reducing drag. This reduction in drag translates directly into improved fuel efficiency, with winglets capable of reducing fuel consumption by 3 to 7%, depending on the aircraft type and flight conditions. The concept of winglets emerged from NASA's research in the 1970s, led by aeronautical engineer Richard T. Whitcomb. Whitcomb drew inspiration from observing how soaring birds curl their wingtip feathers upward to reduce air resistance and increase lift. Following the Arab oil embargo of 1973, when fuel prices skyrocketed, NASA initiated the Aircraft Energy Efficiency Program to develop fuel-saving technologies. Whitcomb's winglet design proved highly successful during testing. The first winglet test flight occurred on July 24, 1979, using a modified Boeing KC-135 aircraft. Over 48 test flights, winglets demonstrated a 6 to 7% increase in fuel efficiency. The first widespread commercial application came with the Boeing 747-400 in 1988, which featured winglets that contributed to a 3.5% increase in range over the previous 747-300 model. While fuel efficiency remains the primary advantage, winglets provide several additional benefits. They extend aircraft range without requiring additional fuel storage, allowing airlines to reach destinations previously out of reach or to carry more payload. Winglets also improve takeoff and climb performance by enhancing overall lift characteristics. From a safety perspective, winglets reduce wake turbulence intensity, which allows aircraft to operate with closer spacing at airports and reduces the hazard posed to following aircraft. This benefit can potentially increase airport capacity and operational efficiency. Today, winglets have become standard equipment on virtually all new commercial aircraft. Different aircraft manufacturers employ various winglet designs, including blended winglets, most common on Boeing aircraft, sharklets, Airbus terminology, and split scimitar winglets on newer Boeing 737 models. The technology has also expanded beyond commercial aviation to business jets, military aircraft, and even some general aviation planes. The environmental impact has been substantial. Since their widespread adoption, winglets on approximately 10,000 aircraft have saved over 16 billion gallons of fuel and reduced CO2 emissions by more than 150 million tons. This represents one of aviation's most successful fuel-saving innovations, demonstrating how relatively simple aerodynamic improvements can yield massive environmental and economic benefits across an entire industry.